Hello students. In this video, we are going to learn about that how to calculate the electric field at a point due to a spherical charged shell, right? So let us start. Electric field due to charged spherical shell, right? So let us draw a shell and let's define its radius. So let the radius be r, and the total charge we give to this shell is distributed on its surface. So the charge is distributed on its surface, and this is Q. So Q is the total charge on the shell, right? R being the radius. Now, let us take a point where we want to calculate the electric field for this, right? Now, what is the concept? We are using Gauss law. So we are going to enclose this charge and through a surface which is going to pass through this point. So what will happen? We are going to draw a Gaussian surface right? And this Gaussian surface is a sphere, and let's suppose this has a radius small r from the center. Right? Now, the concept is to calculate the electric flux. For that, we need the electric field and the area vector at that given point. So the point P, we are having the electric field radially outward because the shell is positively charged, and if we draw a area dA, then the perpendicular to this area, as we know, is the area vector. Right? Now let us apply Gauss law. Let us calculate the electric flux first. So electric flux is equals to E dot dA. The total electric flux, if you are calculating, then it is going to be the integral, and this is equal to E integral of dA. The angle between E and dA, as you can see, is 0 degree. They are in the same direction. So E dot dA is E dA cos 0. So E is constant, it comes out, and integral of dA, it will be the total surface area of the Gaussian surface we have chosen. This is the Gaussian surface, the dotted sphere. This is the Gaussian surface because its purpose is to enclose the given charge. So electric flux is equals to E, and this is 4 pi r squared, the total surface area of the sphere. From Gauss law, as we are doing the application of Gauss law, from Gauss law we know that this electric flux is equals to the charge enclosed. The total charge enclosed is Q by epsilon naught. So this implies that E times 4 pi r squared is Q by epsilon naught. So electric field is 1 over 4 pi epsilon naught Q by r squared. This is quite similar, in fact, identically similar for a point charge Q, where at a distance r, you are going to calculate the electric field for this, right? What if this point is taken on the surface of the shell itself? So on the surface of the shell, this small r, if you carefully see, this becomes equal to capital R. So the electric field becomes 1 by 4 pi epsilon naught Q over r squared, right? Let us consider a point inside now and let us see what happens. If we consider a point P dash inside, want to calculate the field there, we will draw a Gaussian surface. Let's suppose the radius is r dash. The same logic goes. So for a point P dash inside the charged shell, as we see, the total charge enclosed is 0 because the charge only resides on the surface of the charged conductor. We have taken the point inside, so now this Gaussian surface inside, which is passing through the point P dash, is enclosing no charge at all. So charge enclosed is 0. Therefore, the electric field, the dA integral will be 4 pi r dash square. It will be charge enclosed 0 by epsilon naught, which is 0. So this implies that electric field will be 0 inside, right? If we kind of plot this situation into a graph, we can see that we get this kind of a graph between electric field and the distance r from the center of the shell. This is E and this is R. So if we, let's suppose we mark a point which denotes the radius of the shell, then before the radius, that is inside the shell, as we saw, the value is 0. So it will be marked like this. Electric field will be 0. And then at R, it will be having a maximum value. This value, which is electrostatic constant K Q over R squared. After that, as we move out of the shell, it varies as 1 by R squared. 1 by R squared variation. So it looks like this. Electric field falls as 1 by R squared. Right? So what we have learned, that the electric field due to a charged spherical shell outside varies as 1 by R squared. On the surface, it is maximum, and inside it is 0. Right? I hope you have understood this small, easy and simple topic. Right? Thank you and bye-bye.